So question 1 is talking about this 2,2,3 trimethyl butane molecule, which if I draw quickly, we have methyl substitution twice on the second carbon, and then methyl substitution again on the third carbon. So we're looking along this carbon 2 to carbon 3 bond. Okay, from this kind of angle, and looking at the groups which are attached. So on carbon 2 there's 1, 2, 3 methyl groups, and on carbon 3 there's 1, 2 methyl groups, and then of course a hydrogen coming off. So looking at one I prepared earlier, this is what our lowest and highest possible conformations look like. The lowest one, of course, into this staggered conformation to try and keep those bonding pairs of electrons as far away from each other as possible. So let's think about some of the energies which are involved even though we have this staggered conformation. And when we're looking at staggered conformations, we're normally looking for a gauche strain, which is 3.8 kilojoules per mole at a time, a 60 degrees angle, which puts CH3 groups next to each other, too close for comfort, and has bonding electrons repelling each other. So we have 1, 2, 3, 4 examples. So that's 3.8 kilojoules multiplied, of course, by 4. So the total strain energy of this molecule is 15.2 kilojoules per mole. And that's at its lowest energy conformation. When we look at the high energy conformation, we're looking at the bonding pairs of electrons being eclipsed behind each other, and therefore the atoms are eclipsed behind each other. We have a CH3 to CH3 interaction there, which is of course 11 kilojoules per mole of energy. A second CH3 to CH3, which is another 11, and then the hydrogen to the CH3, bit less of a problem, but still 6 kilojoules per mole. So our total for this one becomes 28 kilojoules per mole. So there's our two answers, 15.2 and 28 kilojoules per mole of pure strain energy in these two conformations. So let's take a look at this second problem on page 1. And we've got this trans 1-bromo 3-methyl cyclohexane molecule. And we're going to put the bromine into the axial position. So we need to draw our 6-membered carbon ring first. So as usual, we'll draw two parallel lines which are sloping down, and one of those lines is slightly ahead of the other. And for the direction where the lines are sloping down, the end carbon is going to be up from that position. And then as the parallel lines slope up, you want the last carbon on the other side to be in the relatively down position, like that. So it gives us that undulation back and forth of the 6-membered carbon ring. We want the bromine to be in an axial position, so let's use this axial position in the corner, pointing straight up. That gives us our bromine atom. We also want the methyl group to be on the third carbon, so 1, 2, 3, so this carbon here. And we want this molecule to be trans, so the methyl group has to be trans and on the opposite side of the ring to the bromine. So to get it into a trans position, remember we have an axial hydrogen here pointing up. So the trans position on this carbon has to be the equatorial here, which is sloping slightly down from the plane of the ring. So it gives us a 1-bromo 3-methyl cyclohexane, and they're in a trans configuration to each other. Now the problem doesn't ask about energy strain, but if we were thinking about energy strain, we've got two examples of strain in this molecule, and they're both 1,3 diaxial examples. The strain here between the bromine and the hydrogen, and then the strain here between the bromine and the hydrogen. And both times it's just 1 kilojoule per mole of strain energy. So the total strain energy in this molecule is 2 kilojoules. Remember, the CH3 group, which is in an equatorial position, it's in a staggered conformation to the hydrogens on this carbon here. Hydrogen there, and a hydrogen equatorial there. But this time equatorial above the plane instead of below the plane. So this staggering gives us zero strain between those groups. Let's look at the next problem. Okay, let's look at page 2 and this cyclohexane derivative with the strain energy around the ring. And let's deal with the 1,3 diaxial strain energies first. So we have a ethyl group in the axial position here. It's axial to the hydrogen here and the hydrogen here. So it's a 1,3 diaxial strain each time. These two examples are 4 kilojoules per mole of strain energy. We also have some 1,3 diaxial strain on the underside of the molecule between the bromine and the hydrogen atoms. So there's a diaxial strain there and a diaxial strain there. And these ones are 1 kilojoule per mole each time. We also need to think about our staggered strains, our gauche strains in the molecule. And we have two methyl groups which are in the equatorial positions, staggered by 60 degrees, but that still gives us problems. So there's a gauche strain there of 3.8 kilojoules per mole. Take a last look around the molecule. Everything else should be just hydrogen strains. So a total strain 4 plus 4 plus 1 plus 1 plus 3.8. That gives us 13.8 kilojoules per mole of strain energy. Moving on to the last problem on this page, we're asked, briefly describe and explain if the bias strain theory explains how we get the strain energy from cyclopropane. So a cyclopropane molecule with 3 carbons in the main ring. That 3-membered ring gives us a bond angle each time of 60 degrees, and we get hydrogens above and below the plane which are stuck in an eclipsed conformation. With restricted rotation, we've got hydrogens eclipsing hydrogens, hydrogens eclipsing hydrogens, and hydrogens eclipsing hydrogens on the bottom of the ring as well. So it's 1, 2, 3, 4, 5, 6 examples of this kind of eclipsing strain. And it's hydrogen to hydrogen each time, which is 4 kilojoules per mole. So total strain energy, we said, would be 24 kilojoules per mole. So the strain energy of this molecule is something like 115 kilojoules per mole, much greater than the torsional strain that we see here. So we can say that the bias strain theory is actually correct for cyclopropane. Most of the strain energy comes from this reduced bond angle of just 60 degrees. Electron bonding pairs are much too close to the adjacent electron bonding pairs. Remember, the comfortable angle for a tetrahedral carbon is a bond angle of 109.4. This angle has almost been cut in half. So the bias strain theory explains very nicely most of the strain in cyclopropane